Let's continue talking about op amps, and now I want to look at circuits that have impedance or AC kinds of signals, where we have inductors and capacitors. So essentially, the game is exactly the same. We have an op amp, we have maybe inductors and capacitors, things with impedance in the feedback or in the input. Well, we go through the same things. So feedback, yes. V plus, can we calculate? Yes. That's going to equal V minus. There's going to be no input currents into the inputs. And so we can find IN. Then we can find the feedback resistor. So then we can find V out. So you can go through all the steps that we've done. It's exactly the same. And in this case, it's set up like an inverting amplifier. And we find that the gain is really just minus the impedance of the feedback minus the impedance of the input times the input voltage. Okay, and the gain is just going to be minus the feedback impedance minus the input impedance. So in some sense, like we found before, it's all the same, especially if we use complex notation. Okay, so there's two circuits that we want to look at right here. One is the integrator. So we saw this. We built a simple one for, or I guess that was the differentiator in the homework. Okay, just using a high pass and low pass frequency or filter at low and high frequency. So we saw that before, but this is sort of a more true integrator here where we put a capacitor in the feedback, we have a resistor in the input. You can go through all the things we just said. The gain is V out over V in. We can write down what the impedance of the capacitor over the resistor, and we just get that the gain is minus 1 over j omega RC. And it turns out this is really what we mean by an integrator. Okay, because we said that if you have a varying signal, and we can write it as e to the j omega t, then integration and differentiation just become multiplication and division. In this case, we're dividing by the constant j omega, and so then Vn over Rc, Vn over j omega is just the integral of the input voltage. Okay, so there's no frequency limits. It just works, right? So this is better than using the low pass filter at high frequency. All right, the other one is the differentiator. We just switch them. The capacitor's on the input, the resistor's on that feedback. We can find the gain. It's going to be minus j omega RC. V out is minus j omega RC times the input voltage. And for all the reasons we just said, that multiplication times V in becomes differentiation. So minus j omega V in becomes dV and dt times some constant. So we can differentiate the input signal using this circuit. You can also do a high pass and a low pass filter with gain at the same time. Again, you can go through and do our cookbook and figure out the answers. We'll just cut to the chase here. V out over V in is minus the impedance of the feedback over the input impedance. We can write down that algebra, and then we get a term that looks very much like what we wrote down for a high pass filter before, times inverted and multiplied by some gain. Okay, so we can get the same high pass filter behavior and frequency, and then multiply it, make it bigger, make it smaller, whatever we need to do. And we can do the same thing with the low pass filter. We can calculate the gain. We get a part that looks like the inverting amplifier, and we get a piece, I guess I should go down here, we get a piece that looks like the low pass filter from before. Same low pass filter, but with gain.